Let's do a few additional practice questions that involve equations with logarithms. Before we do so, what we want to do is just kind of highlight the key properties of logarithms. If you remember, this is for going back to section 5.3 in the class. We had three main properties of logs. We called them the product rule, the quotient rule, and also the power rule. And I kind of wrote them a little bit differently than I did in the notes, where I kind of flipped the equations around. Because generally speaking, this is how you're going to apply them whenever you have like a logarithmic equation, is that usually we have to go through the process of condensing a log. For example, if you just look at the product rule here very quickly, one of the things that we know is, every equation has two sides. And so it allows us to, on one hand, when we presented this in the notes originally, you can take a single log base b of m times n. We can split that apart into the sum of two logs. It's log base b of m plus log base b of n. And we said that that was expanding. So if you kind of use this equation going from right to left, you'd be expanding the expression. Okay. On the other hand, and this is oftentimes what you might need to do in this section 5.4 when you're working with log equations, is if you have two logs, what we would like to do is condense them into a single log, like this. So if you have two logs of the same base that are being added together, we can make that the single log of the product of the values. So it's going to be log base b of m times n, and we call that condensing. The idea behind condensing is you want to take an expression that has more than one log term with it, and then create it so that it's just a single logarithm. Very similarly, we have the quotient rule. So if you have two logs of the same base that are being subtracted, we can condense that into a single log where it's going to be log base b of the first value divided by the second value. And it's important to note, I see a lot of students will sometimes make a mistake on this. They'll try to do something like log base b of m divided by log base b of n. That is not correct. Okay? So it's just a single logarithm, and the division that's going on here, by the way, is taking place inside the log. So that's log base b of m divided by n. And then lastly, we had the power rule, which says that if you have an exponent on the inside of a log, you can bring that exponent out in front as a multiplication. Conversely, if we have a factor or something that's multiplying outside of a log, one of the things that we would like to do is to clear off that coefficient. We can bring that inside of the logarithm as an exponent of our value. So p times log base b of m, that's the same thing as log base b of m to the p power. Let's take a look at three examples of log equations, and each one's going to be solved slightly differently. So it's kind of important to kind of pay attention to this. The first one, this is log of 3z equals to 2. Notice that there is no base here. So if it helps, we know that this is common log. A lot of times I'll just go ahead and write it out anyway. I'll write log base 10 of 3z equals to 2. The thing that's nice about this is if you look at the form of this equation, what we simply have is we have one log expression on the left-hand side, and then we have a number on the other side. So logarithmic equations like this, if you can rewrite it so that you're in this kind of situation, a logarithm with nothing out in front, just log of some base of a value equals a number, these ones can be solved by converting them to exponential notation. So this is the same thing as saying the base, which is 10, to the exponent 2 equals the value, which is the part on the inside of the log, and that would be 3z. And then from here we can just solve for z. 10 squared is 100, is equal to 3z. And then lastly, divide both sides by 3, we get that z is equal to 100 over 3. Let's take a look at the next one. In example B, we have log base 4 of x minus log base 4 of x minus 1 is equal to 1/2. Okay. So the goal for this particular equation is we want to kind of rewrite it like we did the last one. What we would like to have is, instead of having two log terms on the left-hand side of this equation, we would much prefer if we could just have it as a single log. And because these two logs are being subtracted, we can do that by using the quotient rule for logs. The quotient rule says that this is going to be log base 4 of the first value divided by the second value. So it looks like this. Log base 4 of x divided by x minus 1 is equal to a half. And now we're back in the same setup we were previously. We have a single logarithm on the left-hand side equals to a number. So to finish it, what we're going to do is let's convert it to an exponential statement. The base is 4. The exponent, which is on the other side, is a half. And that's equal to the value, which is the thing on the inside. That's x divided by x minus 1. And now we just need to solve it from here. We know that the 1/2 power is equivalent to the square root, like this. The square root of 4 is simply 2 over x divided by x minus 1. The very next step to solve this equation, we want to eliminate the fractions. So we can multiply both sides of the equation by x minus 1. X minus 1 over 1 will cancel with this as a factor of 1, so we just get x on the right-hand side. On the left-hand side, we want to distribute the 2 into that quantity. That would give us 2x minus 2. It's basic linear. We get all of our x's to one side. So subtract x from both sides. We get x minus 2 equals to 0. Add 2 to both sides, and we get the solution x equals to 2. One of the things that we discussed in the notes, and you saw this in the lecture, is that with these kind of logarithmic equations, you should be checking your solutions on these. Okay? I didn't do it on this one here, but if I wanted to, I could have. So let me actually go back here and check 100 over 3 is going to be a solution for z. Everywhere we see z, I'm going to put 100 over 3. And then we want to ask the question, is this going to be equal to 2? Well, the 3's cancel, so multiplication by 3, division by 3 cancel. We get log of 100 equals to 2. Remember, this is common log. If you want to, you can explicitly write the base out if it's helpful. And this is absolutely correct. Because if we rewrite it as an exponential statement, this is saying that 10 raised to the second power gives us the value 100, which we know is correct. Therefore, we know that z equals to 100 over 3 is the solution to this equation. A shortcut tip that I also mentioned in the notes, which is also true, is that provided your arithmetic is good, as long as the particular variable value you get will not result on a negative on the inside of a log, then you know the value you came up with will be a solution. Okay? If whatever value you solve for, whether it's x, y, or z, if as a result of plugging that into a logarithm, if it produces either 0 or a negative value, those are things that are outside the domain of the log, and then it would be undefined and it would not be a solution. You could actually get extraneous solutions. So let's go back to this one here. Let's actually check to see if 2 works. Okay. If we have log base 4 of 2 minus log base 4 of 2 minus 1, we want to see, does that equal to a half? Just by quick inspection, all of these insides look good. This is log base 4 of 2 minus log base 4 of 1 equals to a half. This is one of our properties. Log base b of 1 is always 0 because anything to the 0 power is 1. So this is simply log base 4 of 2 equals to a half. And to check whether or not that makes sense, rewrite it as an exponential statement, and that will check out. 4 to the 1/2 power is the same thing as the square root of 4, and we do know that that is 2. So our solution did check out. X equals to 2 works. We'll take a look at one more, which is going to be a little bit different. In example C, what makes this one different is the fact that we actually have logarithms on both sides of the equation. Okay? One of the things that we talked about is that the logarithm is a one-to-one function. So if I'm able to rewrite both sides of the equation so that I have a single logarithm. So if I have log base b of something on the left-hand side equals log base b of something else on the other side, if it's the same log of the same base, then that would apply that the inside parts would have to be equal to each other. So that's the goal. We still want to combine. On the left-hand side here, we can use the product rule to take those two logarithms and convert it into a single log. That gives us log base 2 of x times x plus 2 is going to be equal to log base 2 of x plus 6. Then we just kind of briefly simplify the inside part here. Distributing the x in, you would have x squared plus 2x is equal to log base 2 of x plus 6. And now we're in this situation right here. We have a single log on the left-hand side of base 2. We have a single log on the right-hand side of base 2. And because those two log expressions have equal values, that means that these quantities on the inside have to be equal. So we can drop the logs and just simply put the inside parts equal to each other. That means that x squared plus 2x should be equal to x plus 6. This is a quadratic equation because of the x squared term. Let's get one side to be 0. So I'm going to subtract x from both sides. I'm also going to subtract 6 from both sides. This cancels with this, cancel with this. So we get 0 is going to be equal to x squared plus x minus 6. Luckily, this factors as x plus 3 times x minus 2 equals to 0. If it didn't factor, you could always use the quadratic formula and then set each factor equal to 0 individually. On the surface, it looks like we're getting two solutions. It looks like x equals to negative 3 and x equals positive 2 are our proposed solutions. But again, be very careful with these. Let's go ahead and check these. And I'm not going to plug them all the way in this time, but just quickly notice that if I plug 2 on the inside of any of these logarithms, that should be fine. That'll give me a 2, 2 plus 2 is 4, and then 2 plus 6 is 8. I'm confident in my arithmetic, so that 2 would result in a domain value, so that should work. However, notice what happens if we try to plug in negative 3. If I try to plug negative 3 into this, I get negative log base 2 of negative 3 plus log base 2 of negative 3 plus 2 is negative 1. And on the right-hand side, this would be equal to log base 2 of negative 3 plus 6 would be positive 3. The moment you have a single negative number inside of a log, either from this one or this one, those are going to be undefined for us. So this value, x equals to negative 3, is not a solution. Okay. It comes out in the work, but it actually does not solve the original equation. So we refer to those as extraneous solutions. Therefore, this particular log equation just has one answer, and that's going to be x equals to 2.